Go ahead. Right. Good afternoon, everyone, and thank you for joining us, to the people in person and on Zoom. Welcome to the seminar today. Our speaker today is Michael Perrone. So Michael graduated from WPI in 2017 with a BS in mathematics, with a particular focus on applications of partial differential equations, as well as many supplementary physics and engineering courses. He subsequently worked with Jennifer Lewis's lab at the Weiss Institute at Harvard to spin out Voxelate, a multi-material 3D printing startup based on colloidal physics, work done in that lab. Subsequently, Michael worked at Solvers Global, which is a spin out of WPI, led by Aaron Burt and Sean, whom most of you might know, developing novel air classifying techniques and powder characterization techniques for cold spray. In 2020, Michael started Sandrel LLC to provide material science consulting solutions in areas ranging from piezoelectrics, ion sensing, polymer physics, metallurgy, thermodynamics, and even quantum gravity. So Michael has been tinkering with 3D printers since 2014 and semi-solid printing since 2015. And today his talk is going to be on semi-solid metal printing, the current state, and next steps. And with that, I'd like to hand it over to Michael.
Thanks so much, Aditya. Let's see. So yeah, semi-solid metal printing. Yeah, it's I'll just jump into it. You already heard about me, so I'll skip that. The goal of this seminar is to inspire new research in semi-solid metal printing. The past few years have been relatively quiet after about a decade of attempts by various teams. And I would be very interested in finding grad students and other undergrads who are interested in publishing and collaborating on this, and interested in networking and hearing all your ideas as well. So why would we want to do semi-solid metal 3D printing? Essentially, semi-solid metal 3D printing is attempting to 3D print metal the same way you 3D print thermoplastics. And that's good in a number of ways. Some of the existing technologies for metal printing, a lot of them are powder metallurgical. You need metal powder in one form or another. And there's issues with producing, shipping, and processing metal powders that create oxide inclusions in your parts. And there's a lot of things that complexify powder-based metallurgy. And then the other big process in industry right now is wire arc additive manufacturing, and that's essentially 3D welding. And that has all the normal problems of welding. You have fumes, you have UV light, the metal splatter potentially. And then the resolution you can get out of wire arc is quite limited. So semi-solid metal printing is compact and rugged by comparison if you can get it working. It's essentially using a lot of the same equipment you would with thermoplastic printing. That makes it very compatible with existing thermoplastic software for the most part. And all of that leads to reduced cost, increased usability, reduced hazards. And also because of the capillary action at the interface with the part, it's very insensitive to rocking environments, and you could potentially use it in space, for example. You couldn't do that with powder metallurgy unless you enclosed it somehow and swung it around or something. Anyway, yeah, so there's a lot of features that make it desirable, but it's difficult. So for an overview of the history, I believe one of the first people to attempt semi-solid metal printing, without really knowing they were doing so, was Lulzbot. They 3D printed plumber's solder just because it was the right diameter the same diameter as the thermoplastic they were using at the time, about 3 millimeter. So they were actually able to get a few layers out of that, but inevitably their nozzle would clog. And there was another early experiment. If anyone is familiar with the name of the guy, I can't find it anymore, but someone made their own custom antimony alloy, which they were extruding or trying to extrude. And that was another semi-solid alloy. They eventually gave up on that too. But that was back around 2012, 2013. And then I was collaborating with the Lewis lab at Harvard to develop their 3D printers for voxelate, what would become voxelate. And I realized that the semi-solid metal had a consistency that was very amenable to sculpting and almost like a clay, almost depending. So they were using some silver-based ink, and they were trying to solder to it. Some of the silver ink dissolved completely in the solder and made a semi-solid alloy, and that's where things started. So I came back to WPI in 2015, and I started an undergraduate independent study project where we took semi-solid metal printing a lot further. That was with Perrone Pellion, and that independent study project, we got something basically extruding, and then that was done. That was as far as we got there. And Perrone took that, found some funding, and partnered with Lawrence Livermore National Lab. And also a friend of mine, Richard Everheim, tried to do that for his MQP as well. Both ran into challenges, but Lawrence Livermore did get something printing. And I believe Richard got very close and then decided to do a different MQP or something. I don't remember. It's a tremendous challenge for many reasons we'll discuss shortly. And then Desktop Metal and Stratasys as well attempted to 3D print this way. I believe also 3D Systems at some point, but I wasn't able to find where that was in the timeline. More recently, Oregon State University had what I consider the first successful semi-solid metal prints. They used really a metal matrix composite. It wasn't a semi-solid alloy, but they introduced nickel nanoparticles into gallium metal. And with that, they were able to 3D print various structures. And with it, basically, you produce a fluid with a yield stress. And that's and then there's been more recent efforts in China, but those have also started to peter out. Semi-solid metal printing is difficult because it rests at the corner of 5 different fields, more or less. You have to consider multi-phase fluid flows. You have to consider heat conduction and the phase change of the metal, wetting dynamics at high temperatures, which are very different from wetting dynamics at room temperature, and process microstructure relationships, and then general high temperature mechanical engineering. So the fluid flow is mostly well understood. It's a very developed field. There are some interesting considerations for granular jamming and for the plateau Rayleigh instability. I had a video of this. Unfortunately, I forgot to include it. But normally when you have a stream of fluid, it breaks up into droplets. That's what the plateau Rayleigh instability is about. But when you have a semi-solid alloy, the solid particulates appear to block the droplet breakup, which is very interesting. And then there's a combination of capillary forces and just a kind of defect pinning that prevents the droplet breakup. And that is not particularly studied, but it's very interesting for applications because I was able to extrude in early tests like 20 centimeters, 30 centimeters of wire without anything relieving the strain in the wire. So that's a heavy weight to fight against with the plateau Rayleigh instability. So it was surprising that we were able to get that much wire without pinch off. And if anyone's familiar with the wire production industry, that is you usually use a wire rolling mill, and you roll it through maybe tens, maybe hundreds of times to get really small diameters. So small diameter wire, it needs a lot of processing to get it to that diameter. With this sort of process, you could continuously cast very small diameter wires, which is very interesting, separately even from the semi-solid metal 3D printing. So that I think is worth looking into if anyone's interested. Granular jamming as well is for semi-solid metals not very well understood, I would say. Now, in a semi-solid metal, as you're extruding this thing, it's cooling down, it's going out of the nozzle, and your particles are growing in size and sintering together. And the active growth in the size of the particles exacerbates granular jamming. We have the opposite problem in, well, it's not really, we have the opposite effect in welding, where your material is liquefying and heating up as it's being removed from the wire. And that, I think, may be in some manner analogous to zeta potentials in normal fluids, where essentially your particle sizes are shrinking away from each other, and the interfaces between those particles are the most likely areas where melting will occur next. So the particles tend not to jam in a situation where the temperature is increasing, but in a situation where the temperature is decreasing, it's the opposite case. It's like these particles have an attractive force between each other that helps jamming occur. So that's definitely an interesting analogy to draw that really hasn't really gotten much attention, and again, something worth researching. So anyway, the control of the thermal gradients is mostly an engineering concern for this situation. So finding what the optimal method of actually extruding this stuff is, it just takes iteration, or maybe machine learning, or maybe simulations, or maybe just an infrared camera, but it definitely needs more data. Generally speaking, if you have a long nozzle, it cools off quickly and your material solidifies before it gets out of the tip. Unlike with thermoplastics, the metal has a very high thermal conductivity, and that temperature drop is extremely steep. And the change in viscosity with temperature can be much faster than in a thermoplastic. So all of that, plus the granular jamming issue, means that you need to make sure that that nozzle remains hot enough that the metal can actually get out of the tip and not jam. So that's the main issue there. There's a lot of ways to do this. So you can have a laminated print bed where below the surface, there's some high thermal conductivity material, but at the surface, you have a very low thermal conductivity material, even a ceramic depending. It's the wettability doesn't even need to be that good, as long as it takes long enough of a time scale for that metal to solidify. It tends to stick to the surface. So that's one way. And then making the nozzle shorter, running some electric current, not as much as in welding, but some electric current through the nozzle helps retain the heat. Then engineering your alloy and engineering your print bed temperature and your heater temperature in the nozzle. Because you want your heater temperature and your print bed temperature to be related to your solidus and liquidus of the semi-solid alloy that you're printing. So so that's a lot of parameters potentially to explore, and that's a large search space. So it just requires fast iteration. Luckily, with something that's compatible with FDM 3D printing, you can iterate relatively quickly for relatively cheap. So it's certainly doable. There's been many iterations here. Standard E3D nozzles are too thin at the tip. So even though brass is very conductive, by the time the metal reaches the tip here, it's already solidified. It's already, and that's what Lulzbot kept running into. And you can also use like a fountain pen structure or a brush, and those are very. You can use the geometry of your nozzle, which is inherently unlikely to undergo granular jamming. And you can engineer that as well to reduce the probability of granular jamming, to reduce its severity, and even to knock off material that nucleates on the walls of the extruder, depending, that's all surface chemistry for that. Anyway, high temperature wetting dynamics, I would say there's 8 possible cases, some of which are more common than others. But at high temperatures, material wetting is not like just water on a table or something. These are temperatures for molten metals that are high enough where you can have chemical reactions at the interface. And because of that, it complicates things. So you can have an example like an alloy on an iron surface causes galvanic corrosion at the iron interface. And then eventually the droplet reacts with the surface and then it detaches once the surface is oxidized. So you can have reactive de-wetting, you can have reactive wetting, you can have non-reactive, and then also you can have a substrate which dissolves in the nozzle. And generally speaking, for the purposes of semi-solid metal printing, what you want is either wetting without dissolution or reactive wetting without dissolution. Generally speaking, the easiest to achieve is reactive wetting without dissolution. So for example, molten aluminum is very corrosive under most circumstances. But if you have aluminum metal that's doped with some amount of boron, then you can extrude that through a titanium nozzle and you'll develop titanium diboride at the interface. And that still has reasonably good wetting properties, but it passivates the surface, prevents it from dissolving quickly. So these are the 3 kind of cases, or so there's 8 cases, 3 things that can be the case. Anyway, so yeah, you want your dimensional accuracy of your nozzle to remain constant. You don't want to pollute your alloy with dissolved material. And also your print bed should behave the same way too. You don't want your print bed dissolving into the substrate necessarily. I mean, you can always machine off a part if it's dissolved at the interface. But if you have a material that doesn't dissolve quickly and makes a reactive interface, then you can actually pop the print off just as you would a thermoplastic print. That interface can be a lot more delicate than a normal metallurgical bond. And in this case, you actually want that. You don't want a solder-like bond. So that's something to think about. Yeah, there's a lot of ways to do that. And then the process microstructure relationship. Richard Eberheim actually discovered this very interesting effect in tin bismuth specifically that merits more research, I think. Not for the practical applications of semi-solid metal printing, perhaps, but in general, I think there's some very deep physical insights to be had there. So what he observed was under high shear and maybe under a temperature gradient, tin bismuth tended to usually in a semi-solid metal alloy with dendrites, you break up the solid particles into smaller particles in a high shear mixer or something, or some mixing system. And the breakup of the dendrites improves the flowability and the material properties at the end of semi-solid metal processing. For tin bismuth specifically, for whatever reason, under the right conditions with high shear, the dendrites actually grew, which was very interesting. That's generally not considered possible in that field. So I think as an initial hypothesis, and of course, if anyone's curious about exploring that, please do talk to me afterwards. But as an initial hypothesis, I think in bismuth alloy melts, generally speaking, diffusion rates are very slow because the bismuth atoms are so massive compared to like aluminum or something. They're not actually moving as quickly. The temperature is colder. And yeah, so diffusion rates are slower. And I suspect that under high shear, the interdiffusion coefficients are altered because the shear exposes enough new material that it's actually a larger effect maybe than the interdiffusion coefficients, or of the same order of magnitude. And that it may also be that the specific morphology of the dendrites lends itself to things that stick to each other, like burrs or something stick into your pants. You know, like if it's the right shape, they'll interlock instead of breaking. And then once they sinter together, they're stuck that way. So, and then the granular jamming exacerbated by the temperature gradients. I mentioned that a little bit with the zeta potential thing earlier, but additionally, if this nozzle is cooler than the metal that's coming out of it, you may have nucleation on the nozzle wall. So can you choose your material for the inside of the nozzle wall such that those dendrites don't bond strongly to the wall and are broken off by the fluid flow? Is that possible? Can you alter your nozzle geometry as well to aid that process? So those are things to think about, as well as the zeta potential stuff I mentioned earlier, the analogy to zeta potentials at least. So, and then the other thing for engineering purposes, high temperature metal sealing is critical. Most liquid metals that you might work with, I mean, maybe barring glassy alloys, are very, very low viscosity, lower than water even. So you need really good sealing at very high temperatures, which means you need things that have matched thermal expansion coefficients for the most part, or you need metal-to-metal interfaces. So there's three examples: alumina to niobium, shapal, which is a ceramic from Japan, and graphite. Those are both machinable, so that's easy to work with. Cotronics alumina is castable, niobium is machinable. Lanthanum hexaboride is not really machinable, I would say, but that to tantalum makes a good interface up to even 2000 C, depending on your application. But yeah, so a lot of these are ceramic to metal. Those are nice because you can kind of use threaded material as you would expect for PTFE. So you can add this ceramic and seal the threads of something with that ceramic. And that was this was first attempted, I think, by Richard Eberheim. I tried something earlier. What was the thing called? The company was Expando. I believe it was used on the space station at some point. It's a graphite composite, basically. And that didn't really seal properly. It's really meant for organic solvents and things near room temperature. And I suspect it's just the thermal expansion coefficient of that didn't match. But yeah, alumina to niobium or similar alloys works really well, according to Richard. So new developments, I want to mention this, this picture here. This is from Oregon State University, as I mentioned. The important point about their research is they demonstrate, so they're printing a gallium alloy. So the temperature gradient is almost non-existent. And they're using nickel alloys at room temperature. So the diffusion into the gallium is extremely slow, essentially negligible at room temperature. At least on the time scales they were printing this, for sure. So that slowing of the interdiffusion plus the reduction of the temperature gradient really helps, especially if you can get the print bed to be around the melting point of the metal, or the solidus at least, or even above. So basically, their success there shows that there's a parameter space where this works. That's the fundamental thing there. MIT developed a high temperature fluid pump. I had a picture of it here, actually. They're pumping tin at 1400 C using shapal and graphite here. They machine all the parts, and the thermal expansion coefficients are very similar. And that is, as far as I know, that's the record for highest temperature active pumping, mechanical pumping. Pumping liquid metals, not easy, especially at high temperatures. So there's a lot to investigate next. I mean, we could continue down the road that Oregon State University showed, making a nanoparticle metal matrix composite instead. Also, I want to mention my friend Inigo Anza in the Metals Processing Institute was working with an aluminum nitride and aluminum composite that had similar viscous properties a couple of years ago. And he also suggested printing that composition. Oregon State University's paper proves the concept he suggested at the time. And then, just different process parameters, like having the print bed above the solidus temperature to further alter the temperature drop across the nozzle. Or having the nozzle far enough above the liquidus that the metal remains molten. Anyway, another interesting thing to look at is refining metals by granular jamming. So if you look at this tin zinc phase diagram here, if you have some composition in the middle here, you squeeze out the solid material, there's almost no solubility of the tin and the zinc. So the solid fraction of that you're going to get is essentially pure zinc. And you can do this if there's refractory intermetallics you can do this with. I believe it's called Rio refining in the literature. But if granular jamming is a robust process in these systems, then Rio refining may be a very simple way to get reasonable purity of metals when processing recycled metals, perhaps. You can, for example, you can pull out titanium and nickel impurities in aluminum this way, because the intermetallic compounds are so refractory. And if you can get a semi-solid alloy where the solidification process, the heat of solidification is very large, then you can force it to deliver more heat to the nozzle tip and therefore print more easily. And lower thermal conductivity as well is something to look at. And then the tin bismuth shear agglomeration. And then, of course, the wire production. Continuous casting of small diameter wires from a melt might be very interesting to look at. Anyway, that's everything. And if you have any questions, let me know.
So you said I'm sure about shape ball. Is that a ceramic or is that metal?
Shape ball is a ceramic. I believe it's some vermiculite sort of composite. There's a company in Japan that makes it.
Okay.
Yeah. Anyways, yeah. If anyone wants to work on these topics.
Oh, okay.
It's like the post-processing and press technique versus other powder techniques.
So the post-processing techniques for this sort of thing are fairly negligible. They would be comparable to thermoplastic printing. But also there's new developments in thermoplastic printing. The Prusa XL printer and the E3D tool changer should shortly enable additive subtractive machining in a reasonably priced platform. So you could do additive subtractive. You'd probably have maybe support structures that you would remove. But yeah, very similar to thermoplastic printing in general.
Thank you.
So we have an online question from Sarah. So Sarah, you could just unmute yourself and ask.
All right, yeah, I actually have two questions. Can you hear me?
Sure.
Okay, yeah, so one is, what do you think about these powder filament 3D printing methods? And then the other question has to do with this semi-solid is, do you envision this working at some point for an alloy like, say, steel, like common metals?
Yeah, I see a roadmap in terms of the ceramics available and the coatings available, that you can have a refractory nozzle that can handle those temperatures and not dissolve in the metal. It is a big engineering challenge, but I think it's solvable. So in terms of what was the
In terms of more common metals like steel.
Yeah, so yeah, steel, for example. So first off, aluminum, I mentioned aluminum with a titanium diborite coated titanium nozzle. You could, for example, with iron, with steel alloys, you could engineer a cubic BCN composite. So it's like a boron nitride that's doped with sufficient carbon that it still wets but doesn't dissolve necessarily in the steel. So you could envision something like that. And for titanium alloys, I don't know. There's a lot of room to play around. And then what was the first half of that though? You mentioned.
Oh, yeah. So, I mean, part of the, I guess, benefits of this is that it can be used with FDM printers. I just wanted your thoughts on the approaches that people are using with the, like the powder that's in the filament.
Yeah, so Desktop Metal and Markforged are doing that sort of thing at industrial scale already. The challenge that they forever face with that sort of system is unevenness of shrinkage of the part. You can address that to an extent by controlling the ovens very precisely, microwave heating, etc., directed to specific parts in the volume, careful temperature tracking. It takes a lot of engineering to address that problem, but it's still not necessarily perfectly solved. You can still have parts that slump, you can still have errors. And I guess at production scale, if you're printing 100 of these at a time, maybe some failure rate is fine. And it's viable. I mean, they're doing it. Again, powder metallurgy has some fundamental issues as well with oxide inclusions, with potentially gas pockets and things. It really depends. The issues depend on the sintering parameters, but there's trade-offs throughout that. And if you can just lower the surface area that you're working with by extruding a wire from a metal melt, then you have to worry a lot less about oxidation and similar concerns, or even just like pieces of binder pyrolyzing and getting stuck in the metal, things like that. There's having the powder binder certainly reduces a lot of the issues associated with powder metallurgy, but it does not necessarily eliminate them. Thank you for the question, by the way. Good questions.
Has anyone tried ceramic nozzles?
I have looked into ceramic materials for nozzles. Generally speaking, ceramic to metal wetting for molten metals is poor. You need a ceramic that has metallic character. So, for example, the borides or carbides. Titanium diboride, depending on the metal, can work really well. And any transition metal boride, molybdenum boride, chromium boride, chromium carbide. But yeah, it depends. And the metallicity of the ceramic really helps. You need to match your your lattice constants kind of at the interface, or you want to match surface energies, but also at high temperatures, the specific chemistries of the metals are very important too.
Does anyone else have any other questions?
Yeah, I have one other question. You're not doing this in a vacuum, correct? Or have you tried that?
So yeah, processing under inert atmosphere and vacuum definitely enable higher temperature printing. So like if you want to do steel, you're definitely not doing that in air. The oxide formation is way too fast for good interlayer adhesion. But yeah, under vacuum, under reducing atmosphere as well is interesting. As long as there's no hydrogen embrittlement, that really depends on the alloy. I mean, I have the equipment to try that. It's just it adds additional complexity, and tin alloys oxidize so slowly that it's hardly an issue for those. The other thing that's interesting is if you have a very rarefied but still oxidizing atmosphere, because then sometimes the surface characteristics of the oxides on the metal actually can help the printing process. For example, in bridging and in producing wires from these materials, it may be beneficial to have the surface oxidation in order to help prevent the plateau Rayleigh instability. Anyways, I'm perfectly happy to talk to anyone after the talk as well, if they're interested.
If no one else has any other questions, I'd like to thank our speaker, Michael Perrone, today for his talk on semi-solid metal printers, and you can contact him either through LinkedIn, or I can probably put his email in the chat if people online want to contact him.
Sure.
So do you prefer your Gmail or your WPI?
Gmail.
Okay. I don't know if that is correct. Yes. All right. So thank you very much, and we will see you next week. Thank you.
Thanks for coming, everyone.